Hi, my name is Scott Genzer. I am a senior data scientist at Altair Engineering, and I'm very happy to talk to you today about a manufacturing use case that I've been working on for several years with one of my customers named Mativ. We call it scissors to streaming, how to go from an old school way of doing quality assurance to using modern artificial intelligence using Altair RapidMiner platform. It's a quality process use case, and I hope you find it interesting. So first, a little bit about our customer, Mativ, with whom we've been partnered with for many years. It is a specialty materials company, does both filtration and advanced materials. You probably have actually touched Mativ materials many times. For example, if you buy a turkey for Thanksgiving, the yellow netting that you carry that turkey home in is made by Mativ. If you have any water filtration systems in your house, like a water purifier for an ice cube maker, almost certainly that cartridge that is part of that water filtration, the reverse osmosis, for example, is made by Mativ. They make many different extruded polymer products, and we have been partnering with them for a long time to both reduce scrap and to reduce downtime. So the use case we're going to talk about today is reducing startup time and waste in a plant in Middletown, Delaware. And I'd like to talk a little bit about the use case before we talk about the solution that was made using the Altair RapidMiner platform. So the plant there has an initiative right now which has been going for several years to minimize scrap and downtime, particularly when it has to do with changeovers. What they do is they'll produce a product for a week or several days, and then they need to stop the production line, change over to a new configuration, start up that line, and run that line for a while to get their new product in spec before they can produce real sellable product. So that everything they produce prior to getting that product in spec is considered scrap. And all that time that they're using to get into spec is downtime. So downtime, for anybody who's a plant manager, knows that is an hourly rate and very expensive. And scrap, of course, is just money down the drain. So there's a financial motivation. There's an environmental motivation here because scrap, especially with extruded polymers, these are plastics. They're not recyclable. You can't reuse them. And also the cost of raw materials is very expensive. So we're going to go through one particular product that we've been working on using an inline camera system and how we've been able to solve and improve their quality metrics and improve the speed of their quality metrics using the Altair RapidMiner platform. So we're going to talk about one product, which is called Delnet. It's a product sold by Mativ to many customers. It is what they call a thin aperture net. It has very small holes, for lack of a better word. It's about, maybe about a yard or so, a little bit more than a yard wide, maybe 2 yards wide. And production speeds around 100 feet a minute. This is very typical for line manufacturing. And they have certain quality metrics, if you can see in the middle of my slide here. The three that are really most important to the customer, to Mativ, is what they call boss count, as well as thickness and weight. And boss count is basically the idea is where you have two strands. If I move my mouse here, you can probably see it, where you have two strands that intersect. This point of intersection is called a boss. And so their quality metric is that they go and they count how many points of intersection there are in a certain fixed area, and that is what they guarantee to the customer to meet that specification. So that's a boss, again, is just where two strands of plastic intersect. And you can see they have different patterns. And most of the time, they have sort of this rectangular pattern. Sometimes they even have very interesting hexagonal patterns or triangular patterns, all depending on customer requirements. You can see here at the bottom sort of a piece of the Delnet line. You can see here this extruded polymer net here coming through various rollers. And you can see various systems. If you work in a plant, this will look very familiar to you. And the key thing we're going to work on today is we're going to try to go and speed up what has currently been a manual process for measuring these boss counts. As you can see here at the bottom, this is normally done by the operator. And what they do is, I'll show you in the next slide here. I'll show you in a moment. But the picture is that they go and put this netting under an old school, what I call a microfiche, like you have in the old library, and they hold a ruler up to it, and they measure what is the equivalent of 1 inch by 1 inch, and they physically count by hand the number of bosses in a 1 inch by 1 inch square, whether it's the one up here on the top or one here. And it's very labor intensive. It's prone to error. Now, you can imagine how tedious and boring it is to count these points of intersection, but it's absolutely crucial to ensure the quality of their product they sell to their customers. So as they're saying here, the process adjustment, again, moving from one product to another when they have a new product they need to get up to spec, they have to adjust this process for the new product. And that's the largest bottleneck. And they have to tweak these dials to get it in spec. And they can't start producing real material until they actually get it in specification. And that could be, as they're saying here, it could be around 1,000 feet of material, pure scrap, just in the landfill, money and time and environmental impact directly from these startups every time they change products. So you can see here, they do a setup and then they go and start the winder, and then they have to cut a sample physically with scissors. Go to the small lab where they have a microfiche. Whether it passes or not, they can start production, but most likely they're going to have to go and adjust the process, scrap all the feet that they have, start the winder again, cut a new sample, and keep going. And this can take 10 to 15 minutes or longer, depending on what changeover is, before they can actually start to produce quality product. So they've tried many ways to try to improve this using traditional methods. For example, they've tried to hire quality technicians. Very hard to find. They're slow. They've tried a microscope. They've tried other methods. None of them have come to fruition before this solution that we came up with to solve this problem in the plant. And so the solution here is a dashboard. It's actually a large monitor that is mounted. You can't see it on the right in the picture, but that's a picture of the line. But it's this dashboard here that you see is mounted on a large monitor right in line so the operators can see it. And what it's showing you here is it's showing you the boss count in the machine direction. It's showing you the boss count in the cross direction. For those of you not familiar with inline manufacturing, machine direction means that it's the direction in which the line is moving. So if in this picture here, the machine direction would be from the right to the left onto these rollers here. In the cross direction would be what they call across the sheet, where my cursor is. So again, that's what's called the cross direction. This is what's called the machine direction here, parallel to the line, to the direction that the product is moving. And so the way we have developed this new Altair RapidMiner solution is to go and calculate these things very, very quickly and give those metrics directly to the operators so they don't have to stop the line in order to see whether they're in spec. They can adjust it in line while the product is running and reduce their scrap and their downtime by a very significant margin. What you can see here in the next part of the dashboard is that you can see that what they also get is the boss counts across the sheet from what they call the operator side to the back side. So again, on this picture here, the operator side is on our side of the image. The back side is over here. So I guess it'd be front to back in our image here. And you can see that the variation does exist across the sheet, which is to be expected. And that's okay as long as it's within specification and the machine direction. And then here they actually get a time series. And just to be really clear what the massive improvement is, these yellow dots here, the ones that are connected with the line, are the human measurements that they were doing roughly every 4 hours or so. And these purple dots are the ones measured using this new AI system developed with Mativ and Altair our Altair RapidMiner platform. And what you can see is the amazing correlation here, and then so much better information because you see variation that was, all this variation in here between these two human measurements. But you see that the measurement is consistent over time. You can see here that, for example, we believe very firmly that these were actually incorrect human measurements, whereas these were the measurements made by us. And then you can see here variation that was the humans sort of picked up here, but not nearly as granular. For those of you not familiar, this is called a control chart. The green dotted line is the ideal measurement, and the red dotted lines on the top and the bottom are the boundaries. As long as the measurements are within these two red lines, it's considered in spec. So just to be clear, even though you see variation from a manufacturing point of view, all of the production you see here is product that is sellable because it is within specifications. So the goal here was to go and produce this dashboard, which I'm showing you, which allows them to get far more frequent measurements that are at least as good as the human, if not better, and allow them to reduce the stoppages that they were doing historically to get this product up to speed. So I'm going to sort of go now through the more detailed part because it's the part that hopefully some of you may be interested in, how we did it. How did we solve this problem? How did we go and produce such amazing granular detail of this very interesting measurement using our Altair RapidMiner platform? So that's what I'm going to go through right now. What you can see on the right here is sort of a blown up view of one of their products, like I showed you before. And just to remind you what, again, this is we're trying to count these bosses, these points of intersection between two of these plastic strands. And again, in this picture, the machine direction is up and down, and the cross direction is left and right. So we would say, just because you're going to see this notation, so CD means cross direction, MD means machine direction. So if we were to do the boss count of this particular square, we would say the CD is 5 and the MD is 9 because there are 9 points of intersection in this square in the machine direction and 5 points of intersection in the cross direction. So for those of you not familiar with these kind of terminology, it's fairly clear as once you get used to it. So how do we do this out? So this is how we designed an image analysis system. We did it using an existing piece of very, very, very sophisticated camera equipment sold by a company in Germany named Dr. Schenk. It's a multiple camera inline imaging system, which produces phenomenal quality. So again, you can see here that this was actually imagery produced by the Dr. Schenk system. And you can see these, by the way, this is highly magnified here. And you can see the quality of the imagery. And so what we did is we take imagery from this Dr. Schenk system. The nice thing about the Altair RapidMiner platform is we're very agnostic about where we get information, whether it be tabular data or unstructured data such as images. We don't really care. So in this particular case, we are grabbing normal PNG images from this Dr. Schenk system at a regular cadence, and then we're processing it using our Altair RapidMiner scoring agent, which is an on-premise edge deployment based in Linux. And then it's synchronized with the main orchestration engine, which is our Altair AI Hub, which is on this particular instance is on their own Azure AKS tenant. So it's in Mativ's private cloud. Some customers like to do it, actually I would say most actually like to do it in their own private cloud tenant. Perfectly fine as long as there is a Kubernetes availability. And then the data is being pushed and pulled to their own Microsoft SQL Server. And then what you see there is a dashboard that they use called Grafana, which is a nice open source dashboarding solution. Altair RapidMiner's platform also includes its own dashboarding solution called Panopticon, but Mativ decided to use their own for their own purposes. So that's the flow, is that we're going to take the imagery from Dr. Schenk, we're going to score that imagery, and then we're going to have the AI Hub sort of orchestrate these scoring processes down to this agent and also orchestrate the data store to the Microsoft SQL database, and then also orchestrate the Grafana dashboard. You could also probably imagine there's actually lines in between because there are some parts of these dashboards which are talking directly to the AI Hub. There's also other parts that are talking to their Azure blob storage because we use that as well. So lots of components here. And again, it's really the Altair RapidMiner platform is sort of the glue that's pulling it all together. So how does this work? So here what you see is an image of one of these Delnet products, and it may look a little wavy, but that's because you have to zoom really, really, really far in to see anything of meaning. And that's what this bottom image is a zoomed in image of one of their products. And these bosses are just these tiny little black dots that are really almost merging with one another. It's a little clearer in this image. You can see there one at a time. And to go and make these measurements. So really, really, really amazingly high resolution measurements. And again, the goal was to match the specification that the human was already doing. So for example, the specification was always in a 1 inch by 1 inch square because that is what they are contractually engaging with their customers. These contracts have been with our customers for years and years and years. So in this particular product, for example, the spec could be 24, as we say, bosses in left to right, which would be in the machine direction, in the cross direction here, and then some other specification in the machine direction, which would be up and down. And that's what they need to meet. How do we do it? So what we did was we take these images and we rotate them 90 degrees. And then if we rotate them, if we're going to measure in the cross direction, what we do is take this image and we rotate it 90 degrees. So we're trying to measure again up and down. And we're trying to measure these points of intersection. If you sort of zoom in on it and you actually zoom on the individual pixels, and that's what you see here, each cell is the intensity from 0 to 255 of the black and white pixel. So again, if you're not familiar with image analysis, white is 255, black is 0. And so you can imagine, you can actually see the bosses, like there's a boss here, and a boss here, and a boss here, and a boss here. It's just you were seeing increasing levels of magnification. The trick we play is that we decide, if you look at this very carefully, and we sum the intensities going across of every row. So we take this first row here, and we add 255 plus 255, and we add them all the way across, and we get 4402. And if we do that for every row, you'll notice, obviously, it goes light, dark, light, dark, light, dark, light, dark, light. Or in other words, from a data science point of view, it's a time series. And if it's a time series with some periodicity, if it has periodicity, we can find the frequency of that period, if you like. If we have a period, we can find a frequency. Or if we have a frequency, we can find a period. Once we have that period, we can then convert that period into actual distances because we know the line speed. Again, because it's moving at a certain rate, which we know, therefore that light, dark is directly related to the line speed as this product moves down the line. So the trick here is actually we're going to go and convert pixel intensity into a time series problem. We're going to get the period of this periodicity, and therefore we're going to convert period to boss count. Show that in the next slide here. So if you take that strip that I just showed you in the previous slide and you turn it sideways, you can see this is a perfect sinusoid. Light, dark, light, dark, light, dark, like this. We do a simple Fourier transform here. And so what you can see is you get a nice spike right at the frequency. That frequency is in pixels, which is a little strange. If you think about it, we're normally dealing with frequencies in hertz, but actually the frequency actually the period is in pixels. But we're going to do it in 1/, period, which is frequency here. And so you see a nice spike here at about 0.08. And therefore, the period of this thing is 12.5 pixels. And then because we know the line speed, we can convert that to bosses per inch and determine whether or not it's in or out of spec. That's the mathematics behind what we do here. It's really a clever trick that we play to basically be able to go and do actually very, very easy and fast mathematical calculations so we can able to get them very fast responses. We use drag and drop tools to do pixel aggregation with Altair AI Studio tools. We then productionalized it in the AI Hub. We're able to view it in their system on the plant floor. And according to the customer, not our numbers, but according to the customer, they have $300,000 in potential savings and the average volume on average per year. And it's really an amazing system. They rely on it every day. And it's really been a huge success story. Thank you so much for listening. I hope this was useful to you, and good luck with your manufacturing processes.